The mystery of K2-18b, a window into alien oceans and life beyond Earth. Exploring the scientific challenges and far-reaching implications that could reshape our understanding of the universe is no small task. Yet, it is precisely this task that scientists, philosophers, and dreamers alike are drawn toward. The cosmos is vast, and each new discovery has the potential to alter our conception of where we stand in the grand scheme of existence. Among the most recent and tantalizing frontiers is the investigation of K2-18b, an exoplanet that may not only broaden our view of planetary science but also test the limits of our imagination. Let's embark on an investigation of the first tangible image of K2-18b and unravel what this distant world means for our search for life. Located 120 light-years away, K2-18b is a super-Earth within its solar system. In astronomical terms, 120 light-years is close enough to study with powerful instruments like the James Webb Space Telescope, JWST, yet far enough that humanity will never physically reach it in the foreseeable future. The classification of super-Earth suggests a world more massive than our own, one that sits in a gray area between small rocky planets and massive gas giants. Distinguished by its classification as a sub-Neptune, unlike anything in our own cosmic backyard, this planet is larger than Earth but smaller than Neptune, defying conventional planetary categories. This unique status presents a considerable challenge for scientists trying to unravel the mysteries of K2-18b. While rocky planets like Earth and Mars serve as benchmarks for hypothesis building, and distant gas giants like Jupiter and Saturn offer tentative comparisons for understanding this distant world, sub-Neptunes, planets with no familiar counterparts in our solar system, remain enigmas. The data available so far suggests some fascinating theories. For example, K2-18b orbits in the habitable zone of its host star, a red dwarf called K2-18, raising the possibility that its surface may harbor liquid water, similar to Earth's oceans. This fact alone sets it apart from countless other exoplanets that are either too close to their stars and thus scorched, or too far away and frozen. It is crucial to note that K2-18b's orbit around its host star is much closer than Earth's orbit around the Sun. While 1 astronomical unit, AU, represents the average distance between Earth and the Sun, K2-18b is only 18 cents from its star, closer even than Mercury is to our Sun. This proximity means that a year on K2-18b lasts only 13 Earth days. To us, accustomed to 365-day cycles, this sounds almost unbelievable: entire seasons, orbits, and years condensed into less than 2 weeks. Yet, despite this closeness, the planet's host star, K2-18, is a red dwarf that emits less heat than our Sun. This prevents K2-18b's surface from being completely scorched, unlike what would happen under a hotter, more luminous star. In fact, K2-18b's lower stellar luminosity has turned out to be a major benefit as it has allowed signs of vaporized water to be detected in its atmosphere. A groundbreaking discovery, suggesting the presence of biological signatures similar to those we find on Earth. This detection has electrified the scientific community. Water is a necessary ingredient for life as we know it, and the presence of vaporized water molecules in K2-18b's skies suggests a world that may be far more Earth-like than its size and classification imply. This discovery, which furthers the scientific interest in this exoplanet, is truly revolutionary. The fact that methane decomposes rapidly under solar radiation added even more excitement. The JWST also detected carbon dioxide, a more common atmospheric component. However, the combined discovery of methane and CO was exceptional, because the coexistence of these gases often hints at dynamic chemical processes, potentially biological in origin. Even more intriguing, the telescope identified traces of dimethyl sulfide, DMS. Unlike methane, DMS is not commonly found in Earth's natural environment as a geological byproduct. Instead, it is a molecule produced almost exclusively by biological processes, primarily by microorganisms in the ocean, such as phytoplankton. On Earth, dimethyl sulfide serves as a reliable biomarker, a clue to life's chemical fingerprints. Its detection on K2-18b is particularly intriguing because this planet resides around a red dwarf star, an environment known for intense radiation and long periods of stellar activity, conditions often considered inhospitable to life. Yet, K2-18b defied these expectations. It is crucial that the planet receives a similar level of radiation and resides within its star's habitable zone, where temperatures are neither too hot nor too cold for liquid water to exist provided there is a stable atmosphere. In such a case, K2-18b could have temperatures comparable to those of Earth. Although its atmosphere is hydrogen-dominated, which may make its ocean slightly warmer, the proximity to its star is just right to prevent complete evaporation of surface water. This detail is of great importance, especially in light of recent research suggesting that surface water could be a distinguishing feature of exoplanets like K2-18b. Stay tuned, because soon we will dive into revealing details about the mystery of these exotic worlds. In 2021, astrophysicist Niku Madhusudhan, known for his possible discovery of DMS in space, proposed a new category of extrasolar planets in a fascinating paper published in the Astrophysical Journal, Sub-Neptunes Cradled Beneath Thick Hydrogen-Rich Atmospheres. Madhusudhan chose to call this work a water world hypothesis, a name that suggests their watery, mysterious nature. If these so-called water giants exist, they will be radically different from anything we've ever seen before. Though they could be up to 10 times the mass of Earth and twice the radius, they wouldn't behave like a furnace of steam. Yes, they will be incredibly hot, approaching 200 degrees Celsius. But what would define them is an astonishing feature, a colossal layer of water that could represent up to 90% of the planet's mass. Imagine a world where nearly the entire planetary structure is defined by ocean. This vast ocean could, in theory, harbor the potential ingredients for basic microbial life. Their dense atmospheres trap heat from the star, allowing liquid water to exist over much wider range of distances than on rocky planets like Earth. Sub-Neptunes are relatively common, and hydrogen worlds benefit from this extended habitable zone. This makes them ideal targets for the search for life beyond our own planet. Larger planets are easier to detect from far distances, making them prime candidates for telescope-based investigations. Dr. Madhusudhan's research team used the revolutionary James Webb Space Telescope to observe K2-18b, a possible alien world. This tool could be crucial in our search for extraterrestrial life. But there is a challenge. Even with advanced technology like the James Webb, detecting these hydrogen ocean worlds is a difficult task. The key to unlocking the secrets of K2-18b lies in meticulously planned observation blocks requiring a total of 5 hours of observing time divided into 2 separate observation sessions. K2-18b played a crucial role in a celestial event known as a transit, during which the exoplanet passes directly between Earth and its parent star. During the transit, James Webb captured starlight passing through K2-18b's atmosphere. The beauty of this technique lies in the unique fingerprint that starlight carries, a universal language revealing the elemental and molecular composition of the material it interacts with. By dispersing the light into its component wavelengths, just like a prism breaks white light into a spectrum, scientists can analyze these fingerprints to identify atmospheric molecules. If certain wavelengths are missing from the observed spectrum, that provides important clues about specific gases present or absent in the planet's atmosphere. This spectroscopic transit method has become the cornerstone of modern exoplanet atmospheric studies. From that initial dataset, researchers identified distinct absorption features corresponding to water vapor, methane, carbon dioxide, and the particularly rare presence of dimethyl sulfide. The detection of all these molecules combined, especially DMS, marks a pivotal moment in exoplanet research. For decades, methane and carbon dioxide have been considered potential biosignatures. Discovering them is exciting, but often ambiguous because they can arise from non-biological sources. Dimethyl sulfide, however, is widely considered a more reliable indicator of biological activity, at least in Earth-like conditions. Since the known production of DMS is almost entirely biological, the presence of these molecules around a water-rich planet inside the habitable zone of a red dwarf star means that the possibility of hidden life moves from intriguing theory to empirical investigation. However, skepticism and caution remain. While K2-18b's signals are unprecedentedly suggestive, alternative abiotic mechanisms could still explain some of the observed spectra. For example, interactions between stellar radiation and surface minerals, volcanic processes, or photochemical reactions could mimic certain biomarker signals. The pressure, temperature, and composition of a hydrogen-rich atmosphere, unlike Earth's nitrogen-oxygen mix, also complicate interpretations. Understanding these complexities will require follow-up observations. Additional transits observed in alternative wavelengths, particularly mid-infrared, will help distinguish between competing biochemical and abiotic explanations. Complementary observations from other future telescopes such as the Extremely Large Telescope, ELT, or space missions like HabEx or LUVOIR could enable direct imaging, surface mapping, or even detection of seasonal variations. These future instruments will be essential for validating whether K2-18b truly is a living world or a false positive with Earth-like signatures forged by geology. By documenting in exquisite detail the atmosphere of a transiting sub-Neptune, the James Webb Space Telescope